Okay. Let's see. Is there anything else we need to cover? Oh yeah. So there's questions from quiz 3. Remember, relating a confidence interval to a non-directional t-test. So it's a t-test, non-directional, equivalent to a confidence interval. With if you rejected at at this alpha, what would you do at this alpha? Those types of things. So I think we covered that already from during quiz 3. Do you want me to go over that anymore, or yes?
Please.
Okay. So I think on the quiz I said something like I don't remember. Okay, so you do a t-test, non-directional, with alpha equal to 0.05, and let's say you rejected the null hypothesis. Okay. So that means if we made a 95% confidence interval, the t-test with alpha under 5, if we made a 95% confidence interval for the difference between mu1 and mu2, so mu1 minus mu2, what can we say about this confidence interval? Would it contain 0 or not contain 0? So we rejected the null here with alpha 5%. So our 95% confidence interval
Not contain 0.
would not contain 0. Okay, so rejecting the null means we have evidence of difference, right? It also means that our p-value is less than alpha. So if we have evidence of a difference here, we would have evidence of a difference here. The alpha 5% is equivalent to a 95% confidence interval. So evidence of a difference means the confidence interval would not contain 0. If we redid the t-test, this time with alpha equal to 10%, what would happen? Our p-value, is that bigger or smaller than alpha? Smaller than alpha, right? We know the p-value here is smaller than alpha, meaning our p-value is smaller than 5%. So from above, we know that the p-value is less than 0.05. So we also know that the p-value is less than 10%. So we would reject the null. chapter 7, we have t-test for independent samples. Okay, in this case, our null hypothesis is mu1 minus mu2 equals 0, or mu1 equals mu2. The alternative would be mu1 minus mu2 not equal to, greater than, or less than 0, or the alternative is mu1 not equal to, greater than, or less than, okay, depending on how the question is written. Your test statistic would be x bar 1 minus x bar 2 minus, technically minus 0, divided by the standard error, which is s1 squared over n1 plus s2 squared over n2. You look this up. Down here, the standard error. It's always the standard error on the bottom. Look up the t-table with n1 plus n2 minus 2 degrees of freedom. And again, this is approximate, but good enough for us. We had in chapter 8. Okay, I think you guys all have this one down. This one's the most straightforward. So in chapter 8 we had t-test for paired data. And the null hypothesis is that the mean of the difference equals 0, and the alternative being the mean of the difference doesn't equal or greater than or less than 0. Okay. Your test statistic is equal to the average of the difference column. D bar is equal to average of difference column divided by standard deviation of the difference divided by the square root of n. Okay. So this is standard deviation of difference column. And n is number of entries in difference column. Look up in t-table. N minus 1 degrees of freedom. Okay. Then you have independent samples. Independent samples, but CLT may be violated. would mean generally a small sample with outliers present. Okay, in that case, we use Wilcoxon-Mann-Whitney. The null hypothesis would be that the two populations have the same distribution. And non-directional would be the two populations have different distributions. Non-directional, whereas the directional would be, you know, population 1 tends to produce values that are larger or smaller than population 2. Okay, and then for this one, you have to line up the columns. Columns of data from least to greatest. And then count how many in the other column are larger than the current value in this column. Ties are worth 1/2. Okay, and then pick the larger. Okay, so then sum up those values, and then the column with the larger sum is the test statistic. Look up those values in the Wilcoxon-Mann-Whitney table, and the p-values are given next to it. Yeah.
Do we count which ones are larger or smaller?
Oh, are smaller. Smaller, sorry, that was a mistake. Okay, look up in the Wilcoxon-Mann-Whitney table. You'll need an n and n prime. sample, the sample with more numbers is the n. Okay. Larger n is the n. So if any of these sound unfamiliar, if you need me to go into more detail, just raise your hand. So we don't have a symbolic representation for this these hypotheses because this one's a non-parametric test, right? Non-parametric. Okay, so then we have the chi-squared test for goodness of fit. So this can be applied to any categorical data where you have proportions in mind, okay? So the null hypothesis would be, you know, P1 equals, and I'm just making up numbers here, 20% P2 equals 30%, and P3 equals 50%, and the alternative would be at least one of the proportions is wrong. Or if you only have two categories, you could write the null hypothesis is that P1 equals 0.3, which implies if there's for two categories only, you could get away with just writing P1 equals 30%, and that implies because there's only two categories that the other must be 70%. Okay. Implies P2 equals 70%. All right, and in this case, the alternative. So this, and over here, this is non-directional only. Over here, directional is allowed. Okay, you can have P1 less than 30%. Okay. So P1 less than 30% implies that P2 must be greater than 70%. Okay. So when you have only two categories, you can get away with just specifying one. Okay, and then you have your data. You have your observed data. Data is observed counts. For each category. Okay. So you're expected to get expected calculations will be equal to the proportion in the null times the total count. So proportion in the null hypothesis times the total count. Okay. So if you you add up the expected, it should equal the total count, alright? Cause your expected proportions should add up to 1. And then your chi-squared statistic is gonna be observed minus expected, quantity squared over expected, okay? And then summed for, across all categories. Okay, and look this up. In chi-squared table, okay, with degrees of freedom equal the number of categories minus 1. If you have a directional alternative, then your p-value will be half of the tail in what's given in the chi-square table reference table. Is that okay?
Actually, I
Yes.
have a question.
Yeah.
Like, in particular, 9.411 in the homework, the one where there's like a few men or something, and they have to touch the forehead of a woman or something like that.
Okay.
That
yeah.
one stumped me for a bit, like when I got to that one, because I wasn't so sure as in what my probability would be for the null, being that it would be like 1 out of 3
Right.
versus, yeah, so like I really, that's what gets me. It's like sometimes I'm not so sure if I'm supposed to be doing like the observed is supposed to be how many I actually observed out of the total, or yeah, I get those two mixed up a little bit.
Okay. Yes, in that case, yeah, that's it's tough to really specify, right?
Yeah,
It's
that's
supposed to kind of be clear from the description of the problem, where they say there, you know, the man had to touch the foreheads of 3 women, and one was his, romantic partner. So what's the probability that he would just guess the romantic partner just by random chance? Okay, that's because we're comparing, can he actually tell the difference, or is he just getting it from random chance? So the null hypothesis would be he's getting it from random chance, so he's got a 1/3 chance of getting it right. And then the alternative would be he has more than a 1/3 chance of getting it right. I know, it's a little,
That's what throws me off,
Yeah.
is trying to figure out which probability, because I think in that one they also mentioned that I think half of them got it correct and
Mhm.
half of them didn't, or something like
yeah.
that.
So that would be your data.
Okay.
Your data is what happened.
Got
Okay.
it, okay.
Half got it right, half got it wrong. That's the data. Okay, so that's your observed. Your expected would be, if 36 men just went off of random chance, we would expect 12 to get it right and 24 to get it wrong. So the fact that we saw 18 and 18 versus 12 and 24, is that evidence that maybe some men can actually identify their romantic partners just by touch of the forehead? Seems strange, but who knows, okay?
And so the 12 and the 24 for the expected, it would be like, well, the null hypothesis would be 0.33, right?
Null hypothesis.
Like, well, we're looking
Yes.
for the null
So,
probability.
okay, so in 9.4.11, our null hypothesis would be that the proportion, so in here there's only 2 categories, so we can just write the proportion of getting it correct is 1/3. So this is the null hypothesis. This just means, basically they are if they identify it correctly, it's only by random guessing, okay? It's just a result. alternative is that P is greater than 1/3, okay, meaning they can at least there's something that gives them an edge over random guessing, okay? Okay, the data was 18 correct, 18 wrong. Our expected, okay, so we have a total of 36. So our expected would be, correct would be 1/3 times 36. So we're expecting 12 right, and wrong would be 2/3 times 36, 24. Okay, and then you do your chi-squared statistic, would be 18 minus 12 squared over 12 plus 18 minus 24 squared over 24. So this is 36 over 12, so you get 3 plus 36 over 24, 1.5. You get a chi-squared statistic of 4.5. This is one tail, so this is directional. And I would look that up in the table, and I would divide my tail area in 2 because the table gives me non-directional. And in this case, I guess technically I should have checked directionality, see if my data matches directionality, and indeed it did, because here I'm expecting more than 1/3 to get it correct, and that's what happened, 18, which is more than 12. Okay.
Yeah, because I think that what I was getting confused on, I guess, was that with the observed, it's, I think that the book states that it's the probability, the null probability times the total. So
That's your expected. Yeah.
Okay.
Null probability times your total. Yeah.
okay, because and then that's why I was doing the 0.33 times the 36, and I was like,
That's correct, and you would get 12. 0.33
Got
times
it.
12. 36 would give you 12.
okay.
Okay.
Yeah.
Or I guess
I started
11.98 or something.
Yeah, I started switching it. Okay, thank you.
So yeah, when there's only 2 categories, you can just write a P. You don't have to write both, because okay, and then we have chi-squared for independence. Okay, null hypothesis would be the 2 variables are independent. Okay, and then the alternative is they are not independent. It could be, so symbolically, you can write probability of A given B equals the probability of A, or you could write probability of A given B is equal to the probability of A given B complement. These are allowed, okay? Might have to check a few rules, okay? Is this allowed? Does that imply independence? Yeah, this is no, okay? This is no. What actually is happening here, this relationship is that this plus this equals 1, okay? The probability of A and the probability of A complement given B would add up to 1. What about, probability of A given B, should that equal probability of B given A? Is that independence? No, this is also not independence, okay? These imply independence. These do not. Alright. Okay, and then, so anyway, so these ones don't imply independence. Get rid of those. And then, so your alternative, if this is your null, your alternative could be that probability of A given B is not equal to, or it could be greater than or less than probability of A given, if you decided to go with that, you could choose greater than or less than, okay? The greater than or less than, this implies is only allowed for 1 degree of freedom. Only allowed for 1 degree of freedom. Okay, and degrees of freedom for chi-squared test for independence is the number of columns minus 1 times the number of rows minus 1. Okay. So you're gonna have a two-way contingency table. Okay. Then you have your so your observed will be in the table. Well, maybe it's not given in the table. So observed, you should put it in the table. And then your expected is going to be the row total times the column total divided by the grand total. And then you do observed minus expected squared over expected, add it up for everything. What's that up in here? Chi-square table. Alright, when we have ANOVA, okay, just one way ANOVA. Okay. The null hypothesis would be that mu1 equals mu2 equals mu3, et cetera, which all equals the grand mean, may or may not be necessary. Okay, and the alternative, at least one mu different. Or if you use the alternative model, which states that mu1 is equal to mu plus tau 1, then your null hypothesis would be that tau 1 equals tau 2, which equals tau 3, and all of these equal 0, versus at least 1 tau not 0. So the one way ANOVA is we're stating that the means of everything are all the same, or that tau is just the difference between the mean of everything and that group mean. So we're saying that the difference between the group means and the grand mean is all 0. Okay, it's stating the same thing. So all the group means are all the same, or the difference between the group mean and the grand mean is 0. So that's that's what we do for one-way ANOVA. And then we make our ANOVA table. So we have between group and within group. Total. Degrees of freedom is number of groups minus 1. Over here is total number of points minus 1, and this would be number of groups, and number of points minus number of groups. The books call you number of points n and number of groups as I. And you have the sum of squares. Sum of squares between is each group mean minus the grand mean squared times n summed up across groups. I really hope I'm not butchering this. Okay, and over here we have n minus 1 times the group's standard deviation squared summed up. And then the mean squares is sum of squares divided by degrees of freedom. And then your f is going to be the mean squares within divided by, I'm sorry, mean squares between divided by mean squares within. Yeah, my bad. I should double check my n minus 1 there is okay, good. And we have that for ANOVA. And you go and you look up your F lookup in F table with numerator df equal to the between group df and the denominator equal to the within group.
And if it's larger than 140, we just always use 140, or?
Yeah, yeah.
We're not gonna have to do the looking at.
Yeah, I won't give you the, so bring your reference tables, and your reference tables don't include the F table, so I will not have you actually look up in the F table. But I might ask you what's the F ratio, you know, which F table would you look up, or something. I figure if you know how to use the chi-squared and the t and all of these other tables, you can use the F table, right?
So is the bulk of the final exam like basically questions on each step of like each test? Like you would ask us, what is the null hypothesis for this test?
Yeah, yeah. I'll ask variants of that. You know, what would the test statistic? Here's some data. What's the appropriate test statistic?
Would it be in like chronological order of kind of how we learn?
No,
All
that's
over?
there's an element that you got to be able to identify. I'll try, you know. I try to be clear, okay, and I try to make it fair, just in case. Cause I don't want it to be like, if you mess up this problem, like, it's a little impossible to avoid like some interlinking, right? So like there might be like 2 or 3 questions that are interlinked where if you mess up the first question, it might also mess up the second and third one, okay? I'm trying to avoid some of that by saying, okay, regardless of what happened here. If this happened here, then what do you do, and things like that. But I can't do that for all the problems, so there's gonna be some meshing together here. That's just the nature of the subject matter. Okay, and then the last thing is correlation and regression. Okay, so correlation, the correlation coefficient is 1 over n minus 1 sum of x minus x bar squared over standard deviation of x times y minus y bar squared over standard deviation of y, okay? You can factor out the s of x and s of y. And just do the x minus x bar squared times y minus y bar squared. So that's correlation. Alright, is the test for significant correlation. The null hypothesis, rho equals 0. The alternative is that rho is not equal to 0, greater than 0, or less than 0, depending on the thing. And your test statistic is equal to r times the square root. Let's forget this one. N minus 2 over 1 minus r squared. One of these days I'll remember this one. Okay. And then this, you look up the t-table with n minus 2 degrees of freedom. And then, linear regression. Okay, this is our best fit line. Minimizes the squares of the residuals. Okay, and a residual is equal to the actual value, for y, value of y, minus the predicted value, okay, or so E is y minus y hat. The line of best fit, y hat, v0 plus v1x. v1 is our slope, which equals r times the standard deviation of y divided by the standard deviation of x. And the v0 is our intercept. And that is y bar minus the slope times x bar. Once you have that, you can plug in values for x to get what you would predict y to be. Something.
can teach this class in one session.
I can teach it in one session, yeah. Of course, everything makes perfect sense too. No. I think that's it. Any questions? Yes.
Would you say students do a lot worse on the final than the midterm, or about the same?
I will just say this. I'm rarely surprised by the results of the final. Okay? So,
According
I mean,
to the
yes.
individual.
according to the individual's past performance in the class,
Okay.
I'm rarely surprised. Yeah, I have been, right? I have been surprised by a few students who, in both directions, right? Who have done well the rest of the quarter and for some reason on the final did much more poorly than I expected, and then other students who maybe have done only so-so, but then they did very well on the final. But in general, past performance, everything taken into account, the midterm, the quizzes, pretty good indicator of what happens on the final. I don't know, I probably could do a correlation study on the quiz and midterm average versus the final. I haven't done that, but I have enough data to do something. Yeah. Yes.
Just to clarify what you said earlier about what was tested on the midterm. You said no calculations, right?
Yeah, there's no calculation stuff, just like a few.
Is that more of the conceptual stuff you're telling us about? Or?
Yeah, maybe like a few conceptual stuff. Let me can I ask that is kind of similar but not exactly. Like if I just throw out their a histogram is for what kind of data? What would you tell me?
Discrete.
Numeric data, right?
Oh,
They're just
Oh, okay.
something like that.
something simple, okay. Histogram for numeric data. Or
See, the problem with that question is that you didn't give us any
oh, I didn't give you any options. Okay, I didn't give you any options. Alright, so your options for this question will be applies to experiment only, applies to observational study only, applies to both, applies to neither. We use placebos in this kind of data gathering thing. What's the answer there?
Oh, both.
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 Placebos apply to experiments only. Experiments only.
Wait, but if you're observing the data, couldn't there have been a placebo using the data you're observing?
No. Like when you set up something, if there's going to be a placebo involved, it's an experiment. You would never have a placebo in an observational study. Okay. Well, okay. So stuff kind of like that. All right. So.
This might be too specific and you can refuse to
Okay,
answer, but
sure. We'll choose.
like what percentage would you say would be like calculating p-values versus identifying the null or the alternative?
Oh. I have no idea. And that's not even like I'm unwilling to answer, but there's some you're gonna have to do both. Okay? I don't know how much is how much, okay?
It won't be like 98%.
No, it's probably fairly even would be my guess. Okay. Alright, well that's it. Oh yeah, one more question.
So would you say the questions are very similar to the past quizzes, or would you say it's tougher or longer?
I would say similar. I mean, I write the quizzes and I write the final exam, so it's all coming from my brain. So it's hard for me to really change up the kinds of questions I'm going to feel like I've given you a pretty good idea of what to expect. Okay. So good luck as you guys study. We'll see you guys next week.